Hello and welcome back. In this video, we are going to look at how to load CSV data into TensorFlow. And to get started, there are two main methods that are described in the docs. And here is the link for this particular code that we are going to look at. And I'm simply going to copy the code that's in the docs and try to explain it as we go through it. The very first point that we need to note here is loading the data of the disk. So that's one way, loading the data of disk. And the second is preprocessing it into a form suitable for training. Preprocessing the data into a form suitable for training. And as usual, in this particular series, what we'll do first is set up the libraries that we need to import. So the first section, let's create a section setup. And here we'll import the libraries. Import pandas as PD, import numpy as np, and then we'll set the precision for the output for numpy values by setting np dot set underscore print options precision is equal to 3 and suppress is equal to true. So this way we'll get the numbers in a regular float format and not with the e. And after this we'll import TensorFlow. Import TensorFlow as tf, and then we have from TensorFlow.keras import layers. And with all these libraries imported, now what we'll do is we'll start importing the data into the memory. And the first section that we have here is in memory data. So let's create a heading for that, in memory data. And for this, we are going to use the Abalone dataset. And if you go to Google and look in the UCI machine learning repository, I'm going to put this here. And this is the dataset that is available, Abalone dataset. So if you go to the data folder, this is the abalone.data file that you could download, and we'll be downloading it directly using the web link, and there is some information on what the data set is about. So we'll directly go ahead and download that. So abalone underscore trend. So data set has to do with identifying the C shells based on the characteristics. Is equal to pd.read underscore CSV, and here we'll specify the URL https://storage.google.api.com/download.tensorflow.org data abalone underscore train.csv. And this is earlier I said we are downloading it from UCI machine learning repository. Could do that, or in this particular case we are going to download that from the Google APIs.com resource. And the names that are there for the columns is names is equal to, and we provide the list of column names, length, and I'm going to use the same case that's in the doc, so capital L there, diameter, then we have the height, and after height we have the whole weight of the shells, then we have a shucked weight, and after that we have the viscera weight, and following that we have the shell weight, and finally we have the edge With this, we can look at the head. So Abalone, we can print all the usual characteristics that we read when we import a CSV file using pd.read underscore CSV in pandas. So for example, we can look at the shape. So let's look at that shape, which is Abalone underscore train dot shape. Then of course we know that it's a data frame, but still we can look at the type Abalone ab, and this is given Abalone underscore train, and this is the type we are going to look at, type Abalone, again Abalone underscore train dot, that's all we need. And then after this we can look at the head, couple of rows from the top of this data frame, Abalone underscore train dot head, and let's look at top 3 rows. And we should see this data frame. So here is the data frame. We have 3320 records with 8 columns, and these are the 8 columns that we have. We can also look at the type. So if we look at Abalone dot the types, we should see how this should be underscore train, and we should see the type for each of these. So after importing the CSV file, we see that it was automatically uh, detected as float and integer values for the float values for all the columns except the age, which is detected as an integer. Now in this particular data set, the task is to, so the task in this particular data set is to predict the age from the features, predict the age from the features that we have. So length, diameter, height, and the weights that we are given. So using these features, we need to predict the age for the Abalone. And for this, then what we can do now is get the separate the features from the target. Abalone underscore features is equal to Abalone underscore train dot copy, and then we are going to remove the pop out the age column from that. Abalone underscore labels is equal to Abalone underscore features dot pop, and we say capital A age. And now when we look at the shapes, so print Abalone underscore features dot shape, and if you look at print Abalone underscore labels dot shape, we see that we now have 7 columns instead of 8 columns that we had earlier, and that's because we removed the age column. We can now convert the features that we have into an array. So convert, and that's what we'll do. So convert features into, put features into a NumPy array. And for this we write Abalone underscore features is equal to np.array Abalone underscore features, and then we have Abalone underscore features, and we should see this is the dataset. We now have it in the form of a NumPy array, and we can still check the shape of this, and the shape is the same as what we had when it was in a data frame format. Next, we'll define a Keras model. So let's do that. Define a regression model. So we'll do write regression model, and this is Abalone underscore model is equal to tf.keras.Sequential open close parenthesis, open close square brackets, and inside of this we'll put the layers dot dense 64 and layers dot dense 1, and that's our model. and we can compile it. So Abalone underscore model dot compile loss is equal to this is going to be tf.keras.losses dot mean squared error and open close parenthesis comma. The next thing we need is optimizer. Optimizer is equal to tf.keras.Keras.optimizers.atom open close parenthesis, and with this we now have the Abalone model created. Now let's fit the model. Abalone underscore model dot fit Abalone underscore features Abalone underscore labels epochs is equal to 10, and this should fit the model. We'll run through the 10 epochs, and finally we have fit the model to this particular data set that we have. And that's one of the ways in which we can use what we did in this case was we use pandas to load the CSV file, and then we split the file using by just removing the column of target and then convert it to numpy, and then use that as an input to our keras layer, and then compiled and fit the model as we see here. Now next what we can do is we can look at the pre-processing of layers, basic pre-processing in the pandas such as normalization. So let's do that now. So I'm going to create another heading, call this basic pre-processing, and here we'll create a variable called normalize is equal to layers.Normalization. And if we look at the type, so print type of normalize, and we see that it's a layer, pre-processing layer that we created, and that is a normalization, and we can apply that to our data set. So we can say normalize.adapt Abalone underscore features, and when we run this we have that attached to our Abalone features, and now we'll use that inside of our sequential models. Norm underscore Abalone underscore model is equal to tf.keras.Sequential open close parenthesis open close square brackets, and we first put the normalize layer, and then we have the layers dot dense 64, and after that we have layers dot dense 1, because we just have one value per row that we are trying to predict. And again we'll do the compile and fit. So norm underscore Abalone underscore model dot compile loss is equal to tf.keras.losses dot mean squared error comma, and then we have optimizer is equal to tf.keras.optimizers.atom, and then we'll fit the model norm underscore Abalone dot model dot fit Abalone underscore features comma Abalone underscore labels comma epochs is equal to 10. And when we run this, there is an error, probably some typo. I'm going to just simply copy this, and just this needs to be an underscore. Okay, and that's how we can add a pre-processing layer to the sequential model and then run the data set that we have. In the case that we looked at earlier, this case, what we had was a relatively simple data set where we just have the numeric values, and we are trying to fit a regression model. Now what we are going to do is we are going to look at the Titanic dataset, which has mixed data types in it. So let's create another heading, and this is going to be mixed. Create this 2 hashes mixed data types, and this is using the Titanic dataset. And for this, again, we'll use the pd.read_CSV to read the dataset. Titanic is equal to pd.read_CSV _CSV, and then the same URL, https://storage.googleapis.com/tf-datasets /Titanic/train.csv, and we can look at a couple of rows from this dataset, and might as well look at the number of records, shape, print, and Titanic, and we know that this is going to be a data frame, print, and then we look at the shape of this, Titanic dot shape, and then we'll look at Titanic dot head, and let's look at the first 3 rows. And here is what we have. We have a data frame with 627 rows, 10 columns, and in this particular data set, these would be the features, and we are going to predict if the passenger survived or not using this first column, which would be the target column. And as you can see, in this case, we have a mixed set of data where we have the strings, floats, and integers. Now, if we look at Titanic.d types, here we should be able to see the different types of data. We have integers, objects, and floats. Now, let's again, as before, we'll separate the features and target. So let's do that. Titanic_features is equal to Titanic.copy, and then copy. Copy there, and then we have Titanic_labels is equal to Titanic_features.pop, and then we have survived. That's the column we are going to separate out, and we can look at the shapes of these. So let's print Titanic features.shape, and then we are going to print the labels. So print the labels dot shape, and we see 1 column less. So we had earlier 10 columns, now we just have the 9 columns, and the same 6 to 7 records in both of them. Now that we have the features and labels separated, one thing that we could do now is pre-process the these strings or these columns separately and then put them back together. Otherwise, because we cannot directly input these values into NumPy tensor and into the sequential Keras model. Another alternative is to use the Keras APIs to create what are called as symbolic tensors. And let's look at what these are. So I'm going to create a couple of examples here, and these are directly from the docs. So it's maybe just type out symbolic tensors, symbolic with C there, and it create a symbolic input. So input is equal to tf.keras.Input, and the shape will put open close parenthesis, and the type is equal to tf.float32. Now So this is the input we have created. Now in this, what we are going to do next is perform a calculation using this input. So calculate using input that we just have created. So we can put the quotations around it, and result is equal to 2 star input, 2 multiplied by input plus 1. And then we can look at the result. So the result, look at the result. And before we do that, let's look at the type of result. Print type result and result itself. And you'll see that this is a Keras tensor, and at the moment in the output we do not see that it has any values, right? And so what we need to do next is type tf.keras.Model inputs is equal to input that we have, and then outputs is equal to result. And we can put this in a variable called calc is equal to, and now we can print type of calc, and then print or just type calc there. And what we see now is that this is a functional. The calc is a functional, and this is the object that we have in that is returned when we type calc. To get the values inside of it, so to get the values, what we need to do is type calc 1, and when we type calc 1, we get this particular value, which is 3.0, and 3.0 because we have an input of 1. So 1 multiplied by 2 is 2 plus 1 is 3, and we can convert this to numpy. So we can say dot numpy, and this is the output 3 that we get. Likewise, we can change the input value. We can say instead of 1, we say the value is 2. So 2 multiplied by 2 is 4, and 4 plus 1 is 5, and that's why we get a 5 here. So this is the setup that we are going to use now on the values that we have up here in the Titanic features. And if we look at what type it is, so if you look at the type Titanic underscore features, we see that it's a data frame. And if you look at Titanic features dot items, and here we see that again we have these items, and we can iterate over this now. So if you look at the type of this, type Titanic items, and this is a generator. And now if we say for name column in Titanic items, a colon, we can say print name column and say break after one loop. What we get is the very first column, which if we scroll back up, this is the first column we have, and that's the column we get in the output. So name has the name of the column, and then the column itself is, these are the values in the column starting with index 0. Next, what we'll do is we'll create an empty dictionary up here, which is inputs. Inputs is equal to open close curly braces, that's the empty dictionary. And within this now, I'm going to delete this, and here we are going to type dtype is equal to column dot dtype. So that's the data type, that existing data type of the column that comes inside. And then we say if the data type, so if dtype is equal to an object, if it's an object, then what we want to do is we want to set that dtype is equal to tf.string, else dtype needs to be tf.float32, tf.float32, and then we can use the create the earlier setup that we had where we created the input right here, the symbolic input, and that's what we'll do. Inputs name, which is going to be the name of the column, is equal to tf.keras.Input with a capital I, then shape is equal to 1 comma, and we close the parenthesis, comma, name is equal to name of the column, d type is equal to d type. So what we are doing in this particular cell is we are taking each row, each column from the data frame and checking if it has if the data type is object. If it is an object, then we are converting it to setting its data type to string, tf.string. If it's not an object, we are setting its data type to tf.float32. And when we run this, we should see in the output, we see the this should be a s. So let's run this again, and we see this dictionary that we have for that is inputs dictionary with the key, which is the column name, and the value is the data type. So this is a string. Value is this, not data type, but value is the symbolic tensor, which is this one. And we can check that if we say type and just say inputs, and if we look at the first key value pair in this and look at this, and this is a Keras tensor that we have created, which is this one. Now what we need to do is concatenate all the numeric outputs together. So let's create a heading for that. Concatenate the numeric inputs together. Okay, and for this we'll use a for loop, and we'll create a variable numeric underscore input is equal to open close curly braces, and is inside of this. So what we are saying is we are creating a dictionary here inside of the curly braces, and we say for name comma input in inputs dot items if input, so if input dot d type is equal to tf dot float 32, then what we need is name colon input, the key value pair. And if you look at the type of this after we run this particular line, so let's go to the end of this line and press enter. So here if you look at print type of numeric underscore input, and if you look at numeric underscore input, we should see the output here, and this is a class dictionary where we have this age with the key, and then that's the value with the tensor associated with it, and then we have number of siblings, parse, fair. So we have 1, 2, 3, 4, which are the numeric values, and if you go back up, we have 1, 2, 3, and 4, and those are the 4 numeric values that we have inside of this inside of this dictionary numeric inputs. And now what we'll do is concatenate these using layers.Concatenate. X is equal to layers.Concatenate open close parenthesis, and then we'll specify list numeric underscore inputs dot values. And now if you look at print, if you look at type of X, and if you print X, we should see that it's a Keras layer. So numeric inputs, it should be an input, or else let's put a S there and then run this again. Okay, so what we have is what we have in the output is a Keras tensor X, and that has the concatenated values inside of it. Now we'll perform normalization. So norm is equal to layers.Normalization, open close parenthesis, and then norm.adapt. We are going to adapt this to np.array Titanic, and here we'll use numeric underscore inputs dot keys, open close parenthesis, and then all underscore, and we'll store all of the numeric inputs in this variable. All underscore numeric underscore inputs is equal to norm x, and then we'll look at again print type of all numeric inputs, and we'll look at all underscore numeric underscore inputs. And so let's see what there's inputs, miss the s there. So here's what we have. We have a Keras tensor, which is all numeric inputs, and it is of data type float 32 because it has all the numeric values in it. Now what we'll do is we'll collect all the symbolic processing units to concatenate them later. So we'll collect all symbolic pre-processing results, and so we create a variable pre-processed underscore inputs is equal to, inside of square brackets, all underscore numeric underscore inputs, and again if we can look at the type of pre-processed inputs and pre-processed inputs, and this is what we have. We have this in a list, and inside of the list we have the Keras tensor. Now next step, what we'll do is we'll again look for the string variables, and we'll see how we can work with the string columns and convert them into one-hot vector. So for that, let's create another heading where we are going to now look at string features. We'll use the input data items. So for name comma input in inputs dot items, and here we'll say check if the input dot d type is equal to tf.float 32, then we are going to continue. So we move on to the next one. Else what we want to do is create two layers. One is lookup is equal to layers.StringLookup vocabulary is equal to np.unique Titanic underscore features name. So what we have here is we are taking the unique names of the Titanic features. So of course these are going to be the ones that are strings, because we are checking here if they are float 32, they won't be included in this. Then we perform the one hot. So one hot is equal to layers.CategoryEncoding, and then inside of parenthesis num underscore tokens is equal to lookup dot vocabulary underscore size. So the size of vocabulary for each column. Then we say x is equal to lookup input x is equal to one hot x, and then preprocessed underscore inputs dot append x, and we append this value up there. And so let's run this, and then here we can look at the pre-processed input. So here we have the pre-processed inputs, which is a list. What we can do now is I'm going to copy that and then put that here and rerun this. So what we now have is a list with 1, 2, 3, 4, 5, 6, 6 tensors in it, and that's belonging to 6 different names that we have. So if we look at the, we could actually go ahead and print the print name here, and then okay, let's print the name. And what I'm going to do is rerun this cell and then go down here and rerun this cell and then rerun this cell. So here's what we have. We have these that are the string columns that are now included, so that went through the for loop to for one autoencoding, and then finally what we have is preprocessed inputs dot append. So what we are indeed doing is we have all these numeric inputs that were already there, and to those inputs we are appending these 5 values. So we have 1, 2, 3, 4, and 5. So these are the 5 values, and that's the original normalization that we see. So here if you look at the name, it's normalization 2. And once we have that, we can concatenate all of these together. So let's create a text box, and we can concatenate all the pre-processed inputs. And what pre-processing we have done is for numeric values, what we did was we did the normalization, and for the strings what we did was one hot encoding. And so preprocessed inputs underscore cat is equal to layers.Concatenate and then open close parenthesis preprocessed underscore inputs, and then we have again this is going to be a layer, and then we have Titanic underscore preprocessing is equal to tf.keras.Model, and in here we have inputs comma preprocessed inputs underscore cat, and this is the same as what we saw in a small example earlier when we looked at symbolic inputs, which was up here. So here we had inputs is equal to input, while outputs is equal to result, and that's what we have up here, inputs and outputs. Okay, so with this, then we can then use the so let's run this first. And there is an error, so let's figure out what the error is. Okay, figure out what the problem was. I forgot to put open close parenthesis here after layers.concatenate. So layers.concatenate, then we have open close parenthesis, and after that we have the preprocessed underscore inputs, and then we have Titanic preprocessing tf.keras.Model inputs comma preprocessed inputs underscore cat. And now when we run this, we are through with that, and we can now look at the model in form of a plot. So to get that, we need to type tf.keras.utils.plot underscore model, and in here we need model is equal to Titanic underscore pre-processing rank dir is equal to lr, and then we have dpi. This can be 72 if you are trying to print it out, you can set it to 300, and after this we have show shapes, show underscore shapes is equal to true, and when we run this we should see, so this is the nice kind of flowchart of the model that we have created. in Keras. Next, let's move on and continue with this. So what we'll now do is create a dictionary, Titanic underscore features underscore dictionary is equal to, it will have name is equal to np.array value, and for name comma value in Titanic underscore features dot items. And if we look at Titanic underscore features underscore dictionary, here what we see now is a dictionary with key value pairs, and each key is a column name, and the value is the all the values in that particular column. So if we now look at a couple, just the first value in each of these key value pairs, we should see that would be the first row in the CSV file that we have imported. So let's go down here, create a few more cells, and run this line of code. Features underscore DICT is equal to for, so for name comma values in Titanic underscore features underscore dictionary dot items, and what we need is just the first set of values, so name colon values, and here we are going to say colon 1, and below this we'll say features underscore dictionary. And so now what we have is each column, and for each column we see the values associated with that particular column. And in what I was expecting here is that these would have converted to numeric values, but in this case for some reason I do not see them converted to these values, so maybe I'm missing something. So let me check and I'll come back. All right, I've figured out what the issue is. Actually, there's no issue. This is good. So what we have here is the features dictionary, and the next task is to use this dictionary as an input and pass it to the Titanic underscore preprocessing. So the Titanic underscore preprocessing, which is what we have created above, which is this model, Keras model, and that will take the inputs for preprocessing. So let's do that. Titanic underscore preprocessing features underscore dictionary, and now what we see is the values that are so if this is a value that was a string, it is now converted into one hot encoded. I think this should be the one hot encoded values. Now what we'll do is we'll build a model on top of this. So for that we'll use def Titanic underscore model preprocessing underscore head comma inputs, and inside of this we have body is equal to tf.keras.Sequential open close parenthesis open close square brackets layers.dense 64, and then we have comma layers.dense 1. So that's the body, and then we have preprocessed underscore inputs is equal to preprocessing underscore head inputs, and then we have result is equal to body preprocessed inputs underscore inputs close parenthesis, and we have model is equal to tf.keras.Model, and finally we have the inputs comma result, which is the outputs result. And once we have the model, we can compile it. Model.compile loss is equal to tf.keras.losses dot binary cross entropy because we are looking at a classification problem from underscore logits is equal to true, and then we have the optimizer is equal to tf dot keras dot optimizers dot atom open close parenthesis, and that's the model that we can compile, and finally we return the model. So let's run that function, Titanic model. Now we can use that model that will do everything for us. It will do the pre-processing and it will create the model, compile it. So Titanic underscore model is equal to Titanic underscore model, that's the function name, Titanic underscore pre-processing comma inputs. So if we look at what Titanic underscore pre-processing is, we can look at the type of this, and as you see, that's a functional. And if we go back up, Titanic pre-processing, we keep going up. So this is the one right here. So that's what we are using for pre-processing. And now when we run this cell with Titanic model, we see that there's an error. Okay, so let's figure out what the error is. Finally figured out what the problem was. There is a typo right here. Pre-processed inputs. I think that's the reason why. So let's change that and rerun this. Inputs. And now if we rerun this cell and run this cell again, let's see if that works. And looks like that did work. Okay. So after this, we can go ahead and fit the model. Titanic underscore model dot fit x is equal to Titanic underscore features underscore dictionary DICT. Y is equal to Titanic underscore labels. Epochs is equal to 10. And this should run through 10 epochs to train the model. And so that's how what we did in this case is we created symbolic tensors that are integrated in the Keras model to use a mixed data type with strings and numeric values. So the strings were not encoded and the numeric values were normalized in the pre-processing step and concatenated together to create a final data set that was then processed by using the model.fit. Next, let's keep going, and we can now look at how we can save this. So let's save the model, Titanic underscore model dot save, and we can save with the name, so let's say test, and we can reload the saved model. So we can say reloaded is equal to tf.keras.models dot load underscore model test, and we can then compare how these two work, like the original and the reloaded one. We'll use the features underscore dictionary is equal to, and within curly braces we'll say for name comma values in Titanic underscore features underscore dict dot items, and from this what we are going to get is the name and values. So we are going to get just one value for each of the keys, and let's type that out, features underscore dict, and that's what we will pass into the two models. So this is the before, that's the original one, Titanic underscore model features underscore dict, and then after that's the reloaded model, reloaded, and again features underscore dict, and here we'll use assert before minus after if that difference is less than 1 e to the power minus 5, sorry, minus 3, and print before, print after, print after. Remove that extra parenthesis, run this, and here is what we have. We have the same values from both the uh, the reloaded model and the original model that is still running in the notebook. So far what we have looked at is the Keras library's built-in functionalities to reprocess the data. So if we need more control, then we can use the tf.data. So for that, let's create a cell here. I'm going to add a section tf using tf.data, and for the purposes of processing, so first section will look at in-memory data on in-memory data, and what we'll do is we'll load this, we'll consider the same dictionary that we have been using previously, and so we'll go ahead and import the iter tools, import iter tools, and below this we'll create a function that will look like this: def slices features, that takes in input argument features, and this is a generator function. As you'll see, we are not returning, but we are writing yield at the end of this function. For I in iter tools dot count, what this does, it's sort of creating an infinite loop, and inside of this we'll create an example is equal to, which is going to be a dictionary, and for name comma values in features dot items, and here the names and values. So we'll take name, and so all the names, and so each iteration will get a name, and we are going to pick ith value from that, and then we are going to yield example. Yep. Now when we use that function right here, for example, in slices, and we pass in the dictionary Titanic underscore features underscore dictionary, and inside there we can say for name comma value in example dot items, print, we are going to print the name and the value. The print name, in the curly braces we say name colon, we have 19 spaces there, close curly braces, colon, space, again another curly brace, value, close the curly braces, and then here outside of this we'll say a break and run this. So what we see here in the output is we are taking each column and one value from that particular column. And next we'll use the tf.data to create slices. So the way we'll do this is as below. We create a variable features underscore ds, so features dataset is equal to tf.data.dataset from underscore tensor underscore slices Titanic underscore features underscore dictionary. And if you look at the print type of features underscore ds and features underscore ds, what we'll see is that this is a tensor slice dataset, and this is what it looks like. So we have the column name, and then we have the tensor, we have the type of the tensor, and so on. Now we can iterate over this feature underscore ds dataset that we have just now created, like so. For example, in features underscore ds for name comma value in example dot items colon print. Again, we'll use the same print f within quotes. We have one curly brace here, colon, then another curly brace there, and inside of the first curly braces we are going to write name colon 19s. In the second one we are going to write value. And when we run this, this is the if we put a break, we'll just get one round of iteration. And if we scroll back up, we have example in features underscore name on this, and then we have this we said break. Okay, so we need this break to be outside of this for loop. Okay, now we are good. So this is what we have, and what we have, what we are looking at is values from the dataset that was created using from tensor underscore slices. And continuing with this, we can combine the features and labels. So let's say we have we can use tf.data.dataset from tensor underscore slices, and inside of the parentheses provide a tuple Titanic underscore features underscore dictionary. So that's the features part of it, and then we have Titanic underscore labels, that's the labels associated with those, and we'll put that in the variable Titanic underscore ds dataset. Now when we look at the type of this will again be dataset, TensorFlow dataset. So if we look at print type Titanic underscore ds, and then look at Titanic underscore ds. So this is the TensorSliceDataset from that we have created, and earlier what we had was the same TensorSliceDataset, because we are using the from underscore tensor underscore slices. And with this we can add functionalities such as shuffle and batch to this particular dataset. And let's say add shuffle and batch to the dataset. And to do that, we'll say Titanic underscore batches is equal to Titanic underscore ds dot shuffle, and length is going to be Titanic underscore labels. And then we are going to also do the batch. So 32 items per batch. And now what we have again let's try to print what the type is, and let's copy this and paste it here. And so what we now have in the output is a batch dataset, as you can see, and these are now the batch dataset elements. Earlier what we had was TensorSliceDataset elements. With this we can now pass this Titanic batches to the fit. So to fit the model, Titanic underscore model dot fit Titanic underscore batches epochs is equal to 5. And now this is how we were able to run the model. So what we did in this case is we use the tf.data from tf.data.datasets from tensor underscore slices functionality, and we are then able to add shuffle and batch to the dataset and then pass that on to the model.fit. Next, what we are going to try start working on is getting data from a single CSV file. So from a single file, and for this we'll create the path Titanic underscore file underscore path is equal to tf.keras.utils.get underscore file, and within parentheses we are going to specify train.csv comma, and up here we are going to specify the URL for that, and the URL is going to be https://storage.google-apis.com/tf-datasets Titanic train.csv. That's the path. So if we type it out, Titanic underscore file underscore path, that's what we get. So this is in the root, located in the root. And now what we can do is use the make CSV dataset functionality to read this. And for that we'll use tf.data.experimental.make underscore CSV underscore dataset open close parenthesis, and we'll assign this dataset, we'll name it as Titanic underscore CSV underscore dataset is equal to this. And within parentheses we need to specify Titanic underscore file underscore path, then batch size is equal to 5, and this is just for demonstration purposes, and label underscore name is equal to survived, and next we have number of epochs is equal to 1, ignore underscore errors is equal to true. And that's how we should make underscore CSV underscore this should be data set. Okay, so this is how we have created the Titanic CSV dataset using make CSV dataset. Next, what we'll do is we'll iterate over this and see what values are inside of this dataset. So for that we'll use a for loop for batch comma label in Titanic underscore CSV underscore dataset dot take 1. We take the first batch, and in that batch we are going to look for key value in batch dot items colon print, and here we'll print two things. One is the key, and then colon will print the value. So let's put the value in there, and for the key we'll put the key colon and we'll put couple of spaces, 20 spaces, and after that outside of this inner for loop we'll just simply type print, and below that print again we have the key value. So I'm going to put a quotation, 2 curly braces here, then colon, 2 curly braces, and the last one will label, and the first curly brace would have the label colon and 20 spaces there. So this label is going to be will be inside of the quotations like so. And when we run this is what we have. We looked at the first 5 values, and so we have these values. Each list inside of here has 5 values in it, and we have the columns written like so. So this is how we were able to use the functionality of make CSV underscore dataset. Similar to this, we can use another method where if we have zip files, then how do we work with those? For that, let's look at this example where we are going to use the again the get file. So here we use the get file utility. That's the same thing we are going to use down here, and we are going to get a new data set, traffic underscore volume underscore CSV underscore GZ is equal to tf.keras.utils.get underscore file, and in here we specify the name of the file, metro underscore interstate underscore traffic with a capital T, traffic underscore volume dot CSV dot GZ, and then we have https://archive dot ics dot uci dot ml uci dot edu /ml/machine learning databases /00492 metro underscore interstate underscore traffic underscore volume, and after that we have the csv.csv.gz. So that's what we have for our data set, and that was successfully downloaded. Next, we'll again use the make CSV dataset. So we'll create the dataset in the name of traffic underscore volume underscore CSV underscore GZ underscore DS is equal to tf.data.experimental.make underscore CSV underscore dataset, and then we'll specify the name of the file, traffic underscore volume underscore CSV underscore GZ batch underscore size is equal to 256, and then we have label name is equal to traffic underscore volume, that's the name of the column that has the target, and then we have number of epochs is equal to 1, compression type is equal to GZIP, and so that's the data set we created. We can now iterate over this data set as before, so why don't we copy this set of lines, paste them down here, and just change a couple of things. Batch label stays the same. Here, instead of typing that, we are going to use this data set dot take one. Again, the rest of it stays the same, and down here we'll say square brackets :5. Okay, and again for values we'll say square bracket :5 and run this. So what we get here in the output again is the name of the columns and the 5 values for that particular column in the output. So this is another way in which we can directly use the zipped file. We can read directly from the zip file by specifying compression type, and the rest of the make underscore CSV underscore dataset will handle the rest of it. Now let's look at the importance of caching the dataset. So let's create a title here, caching, and put some heading. Okay. So for if you look at the time it takes to run these, we'll time this % time, and this will give us the wall time for the cell to run. For I comma batch label in enumerate traffic underscore volume underscore CSV underscore GZ underscore dataset dot repeat 20 : if I %40 is equal to 0, and that is I mod 40 is equal to 0, print or the dot, and end is equal to just nothing there, and we can print this. So print, and after this what we should see is the how much time it took to run through this particular loop and what would happen if we use caching. So I'm going to copy this. While that is running, let's type out the code below this, and for caching is additional line of code. We'll write caching is equal to traffic underscore volume underscore CSV underscore GZ underscore dataset dot cache, and then shuffle 1000, and then this caching is, so we have wall time of 41.1 seconds. We use this caching here, so caching dot shuffle, and then shuffle 1000, and then we have the repeat 20, and the rest of it stays the same. Now when we run this set of code with caching, we should see a decrease in the time it takes. So it just took 3.32 seconds as compared to the method that we had up above. So that's one of the importance of using caching. In addition to caching, there is something called as snapshotting, and let's look at that. So for this, we'll change the name of the variable snapshotting, and this stays the same, except here we are going to say snapshot, and in the parenthesis we'll specify Titanic dot tf snap, and shuffle 1000 stays as is, and here we are going to change this caching to snapshotting. Then we have the shuffle and repeat, which stays the same. When we run this, let's see how much time this takes, and this takes around, again, much less than the very first case where we didn't use any caching or snapshotting as we did here. So according to the docs, so the snapshotting files are meant for temporary storage of a data set while in use, while this is not a format for long-term storage. That's the case with snapshotting. Moving on now, let's look at how we can work with multiple files. Let's say if we have a folder with multiple CSV files in it, how can we use tf.data to build a data set from those files? So create a heading, multiple files, and for this we are going to use the data set of fonts from the UCI machine learning repository. Fonts underscore zip is equal to tf.keras.utils.get underscore file, and here we specify fonts.zip, comma, that's the name of the file. You specify the URL https, and why don't we copy the entire link that we just had up here. So I'm going to copy this and paste it down below, right here. So we have the HTTPS archive IICS UCI ADU ML machine learning repository databases, and the number for this is 417, and the name of the file is simple, it's just fonts.zip. So remove that and type fonts.zip, and after this we are going to specify a few more things, which is cache underscore dir is equal to a dot, and then cache underscore sub dir is equal to fonts. And below that, we'll say extract is equal to true. So that should download the zip file, fonts zip file. And after that is done, we'll go through the folder names that are created. So now if we import pathlib, and below that we'll go through the file folders that are there. So sort for p in pathlib dot path fonts dot glob, and here we'll say star.csv, and all of this we are going to put this in a tuple, and here we'll say sorted, sorry, here we'll say string p, and then we'll sort of this sorted, and again we'll put all of this inside variable name called font underscore CSVS is equal to this. So now if you look at font underscore CSVS and look at the 10 values in there, we should see the names of the CSV files. So these are the names of the CSV files we have, and then if you look at the length font underscore CSV as, so we have 153. So there are 153 such files in the folder fonts, and we want to build a data set based on all of these files. And one way to do that is using make CSV dataset. So what we'll do is create a font underscore dataset equal to tf.data.experimental.make underscore CSV underscore dataset, and here we'll specify the path file underscore pattern is equal to fonts backslash star.csv, comma, batch size is equal to 10, number of epochs is equal to 1, and then we have number parallel reads is equal to 20, and finally shuffle underscore buffer underscore size is equal to 1000. So let's type that 1000, and this is how we have now created the fonts dataset. We can now iterate through this dataset as before, and for that what we'll do is we'll copy the same line of code that we had. So the one right here, I think this was the one. So copy this and paste it here, and then what we are going to few changes. We are going to say this is for the numeric, so this is not the one actually. Or never mind, let's type all of it. Features in fonts underscore dataset dot take one, and then for I comma name comma value in enumerate features dot items open close parenthesis, if I is greater than 15 break, else break, and then what we have is print f, and within quotation we have curly braces colon space curly braces, and in the last one we just type in value. In the first one we are going to type name colon 20s, and the next outside of that loop we'll type print dot dot dot, and below that again another print, and in here we'll specify we'll write again a list that has total colon then open close parenthesis inside of this length features, and then we have outside of the curly braces features. So when we run this now, what we should see is the column names and associated values with that. So there's a typo there, features, and we should see that shortly. And again, the misspelled features, hoping it will run this time. Okay, so here's what we have. These are all the names of the columns on the left hand side, and these are the values associated with the columns. And in total, there are 412 features. There is 412 columns, and the first 12 columns, I think the first 12 columns are, so this is the first one, and the second one, third, fourth, fifth. So these first columns, these are the ones that are different, and then after that there is this pattern with the column names R0, C0, R0, C1, and so on. So what we can do is, these are images of, so each row is image of a font, a font or a character. And so what we need to do now is combine those pixel values to create an image. And for that, what we are going to do is use regular expression to capture those column names R0, C0, now that type. For that, we'll import import RE, not red, just import RE, and below that, we'll create a function that will do that. That will get all the pixel values, put them, reshape them, and we'll have them ready for display. So we'll create a function called make_images, that takes in the features, and we'll create an empty list, with none and star 400. So it's 400 items in it. Empty dictionary, new features, and then for name value in features dot items, what we are going to do is match on the column name. So we match is equal to re dot match, and the pattern we have is this R. We have two groups. We have one group here and then the second group here. So that's the R, which is the R for R, and after R there will be some number there, and then after C there will be some number there. So R0, C0, something like that, and we are looking for that in the name. And if that is the case, so if it is a match, if this is true, then what we want to do is put this value, put the value at a particular location in the list image, and the location is going to be an integer, and the integer is, this is kind of arbitrary, it is created to arrange it sequentially. We are going to say match.group 1 times 20 plus so that's that, and then we say plus int match.group 2, and that should do it. So match.group 1 times 20 plus so this int should be without, int should be there. Then we have the second one, match.group 2, and then we have those values. Below this, then else, if that's not the case, new features, and then name is equal to value. Okay. So with that, so that's that, and then below the, after the for loop, then we'll say image is equal to tf.stack image comma axis is equal to 0, and then image is equal to tf.reshape image comma 20 by 20 pixels comma -1, and new features image is equal to image, and then we return new features. Okay. And now what we can do is apply this function to our dataset, which is fonts.ds. Fonts underscore ds dot map, and we are going to apply make underscore images, and we'll put all of that in fonts underscore images image underscore dataset is equal to this. Okay. And now if you look at print fonts underscore image underscore dataset, and if you look at the type of this, what we see that it's a map dataset that we have created, and we can again go through this one. So for features in fonts underscore image underscore dataset dot take one colon break. And so what we did here was we applied the function to each batch in the dataset. Now we can plot the results. So for that we'll use the matplotlib library here. So from matplotlib.pyplot as plt, from that my mistake there, matplotlib plot, that's my mistake. From matplotlib.pyplot import let's see, from matplotlib import pyplot as plt. Okay, and then we create the figure. Plt dot figure fig size is equal to, we'll create a 6x6 size for that. DPI doesn't really matter right now, but we'll put the DPI as 120. For n in range 9, so we are creating a grid of 3x3 images. plt dot subplot 3x3 comma n plus 1, and then we have plt dot imshow features image, and then 1 2 3 comma n, and plt dot title chr features, again within square brackets m underscore label, and outside square brackets we have another square brackets with an n in it, and plt dot axis, we specify this as off. And hopefully, yeah, so here are the images. So this is the fonts for that we have in those files, and this is kind of visualization of that. And this is number 7. This is greater than sign, and there's some other characters there. Okay, so in addition to what we have seen so far, there are functions called that can be used in TensorFlow that again we can get more flexibility on how we can work with the data. So these are the lower level functions, lower level functions, and there are two functions that we are going to look at. One is tf.io.decode underscore CSV. Next one is tf.data.experimental.C capital CSV lower SV, then dataset with a capital D. So this is the io.decode is a function for parsing lines of text into a list of CSV column tensors, and the CSV dataset is a low level CSV dataset constructor. So to work with this, let's create a variable text is equal to pathlib.Path Titanic underscore file underscore path, and then we say dot. So if we look at just this part, okay, just print this. If we say type of txt, and if you look at txt, this is what we have. That's the POSIX path. That's the, of course, the path we have, and then this is the path that we see. Now if we type in dot read underscore txt, and now look at what we have is this is the data that's inside of that path on inside of that file. And what we can do now is we can split that particular string, this is just one string, on these new line characters that we have. So for that we'll say lines is equal to text.split on the new line, and here we'll specify from 1 to -1. And when we again look at print type lines and look at the lines, this is what we get. We have now successfully split the string into this, and this should be a list now. So if we scroll all the way up to the beginning of this, we'll go down. So that's a list, and each line is an item inside of that list. So if we go down here and say all underscore strings is equal to str square bracket, parenthesis times 10. And what we are trying to do here is we are creating a placeholder as the empty list with strings. So what we are saying is there are 10. So this is 0, 1. So 1, 2, 3, 4, 5, 6, 7, 8. No? So 1, 2. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So for each column we have a different. We are saying that those are strings, and we'll use the io.decode to automatically assign those. So let's do that. Features. Let's type this again. Features is equal to tf.io.decode underscore CSV, and within parentheses we have lines comma record underscore defaults is equal to all underscore strings. So what we are saying is we are taking the lines, which is the list of values, which is a list, which are the values, and then these are the defaults we are setting it to, which is this empty list we have created with string as data type. And so we'll say for f in features colon print f, and then within quotation we have a comma in middle, and before comma we have a double, we have curly braces. After the comma we have curly braces. In the first case we are going to type colon f.dType.name, and in the second case we are going to type shape colon, and inside of this f.shape. Now when we run this, what we see is that each column is now a type string with 627 values in it. We can also print those. So if we print lines, we print the first item in the list lines. This is what we have. Now what we can see is there are integers, floats in there, so we can customize that. We can say Titanic underscore types is equal to, the first one is the integer, so we say int. Next one is a string, so we say string. Next we have float, then we have integer again, then integer, then we have float, then we have string, another string, another string, and another string. So we have 4 strings. And then we can look at Titanic underscore types And this time we see that this is now not all strings, but we have integer, floats, etc. And we can use the same line of code that we did just now use. So I'm going to copy that, paste it here. And what we are going to do this time is use the Titanic types instead of these all strings. So we type Titanic underscore types, and the same features, rest of it stays the same. And when we run this, we see now that we have the type int32, float32 in addition to the string that we had earlier. Next, let's look at how we can use the CSV dataset in these situations. What we'll do is we'll create a new dataset. So let's create a heading first. This is tf.data.experimental.CsvDataset, and we are going to create a variable simple Titanic is equal to tf.data.experimental.CsvDataset, and within parentheses we have Titanic underscore file underscore path, and then record underscore defaults is equal to, and this is going to be equal to Titanic underscore types, Titanic underscore types, the header. The file, the CSV file does have the column names in the first line. So we specify header is equal to true. And so that's what we have for the experimental, for the dataset, CSV dataset. And we can iterate over it. For example, in simple underscore Titanic dot take one colon print, and here we are going to print e dot numpy. So well, let's say, so here's what we are going to do. For e in example, I will convert this to an array e dot numpy numpy and run this. So in the output, we now see that we have this list which has all of the values that are from the dataset simple Titanic. And the code that we just now wrote is equivalent to this particular code. So above code is equivalent to below. So let's type that df decode underscore Titanic underscore line return tf.io.decode underscore CSV line comma Titanic underscore types, and we have manual underscore Titanic is equal to open close parenthesis tf.data.TextLineDataset Titanic underscore file underscore path dot skip one dot map, and we are going to use the function we created decode underscore Titanic underscore line. And below this, then we can iterate over it same as before. So why not just copy that? I'm going to copy that line of code, put that right here, and just change the name from this manual simple Titanic to manual Titanic, and run this. And hopefully we should get the same output, except there is an error. Let's figure out what the error is. tf.data.text, I've missed the T there, so this should be text line dataset, and we get the same output as we did up above. Now in case of multiple files, so if we have multiple files, multiple files, then here's what we want to do is this font underscore line is equal to pathlib.Path from, this is going to be font underscore CSVS open close square brackets and 0. We are taking just the one value, read underscore txt text open close parenthesis split lines open close parenthesis square bracket 1 print font underscore line. So this is what we have. So what we are printing is just one line. Here we can count the number of features by counting the number of commas in there. So let's do that. Number font features is equal to font underscore line dot count within quotes commas and we say +1. Font underscore column underscore types is equal to here we have the square brackets plus the square brackets this the square bracket again square bracket multiplied by parentheses. So we'll plug in the values here. String comma string, then we have float 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 open close parenthesis, and then we have num underscore font underscore features -2. Okay, and here then we can say font underscore CSVS open close square brackets, this is 0, and that's the CSV file. So for row in simple font underscore dataset, take 0 or take 10 and we can print row square bracket 0 dot numpy open close parenthesis. And so these are the names of the fonts we have, records from the agency.csv. There is also an option to use the interleave, so datasets.interleave. To interleave the file, to interleave multiple files, use dataset.interleave. And what we'll do is we'll create a variable font underscore files is equal to tf.data.dataset.list underscore files, and this is going to be fonts by / star CSV. And so the way this works is we'll look at an example how this shuffles what files it picks. So from print epoch 1, and here let's get the files for f in list font underscore files, and we get the 5 files colon print, and here we put some spaces 1 2 3 4, and then say comma f dot numpy open close parenthesis, and then print quotation 1 2 3 4 to 3, and then we have print just the parenthesis. I'm going to copy this, and if we run this the second time, we are going to get a different set of values. So as you can see, epoch 1 we get these file names, epoch 2 we get a different set of file names. Now to use again for the interleave part, what we'll do is we'll create another function, and this function is going to def make underscore font underscore CSV underscore dataset path return tf.data.experimental.CsvDataset, and this would have the values path record underscore defaults is equal to font underscore column underscore types. And then we have header is equal to true. That's the function, and we can now use that function with the interleave. So from font underscore rows is equal to font underscore files dot interleave, and then make underscore font underscore CSV underscore dataset comma cycle underscore length is equal to 3. So that's if we look at the type. So if we look at print type font underscore rows and look at font underscore rows, we should see the output right here. And as you can see, we scroll all the way up in here. So we can see that it's the interleave data set, and these are the elements within it. We can now access those values. So what we can do is create a dictionary. Font underscore dictionary is equal to and again here we are going to get two sets. This is the first one, second one, this is the first one, and we'll say font underscore name colon this, and then this is an empty dictionary with two keys, font name and character colon. This should be a quote. Okay, so that's the dictionary, and we'll use that now for row in font underscore rows dot take 10 colon fonts underscore dictionary font name font underscore name dot append row square bracket 0 dot numpy and then dot decode and then we have fonts underscore dictionary character dot append chr row square bracket 2 dot numpy, and that's that. We can then, so this is going to be a dictionary, and so if we print font underscore dict, we'll have values in the dictionary. So that's the empty dictionary, and we can convert it to a data frame. We can say pd dot data frame font underscore dictionary, and we should see a data frame with values in it, but this is empty. Let's figure out why. I've found a mistake. There was a typo. Instead of font, it should be fonts underscore dictionary. So now when we run these two, we should see values appear in the data frame. Still it comes out as empty. And then there's yet another typo. There should be a S there, and there should be another S here. That's okay. Now this should work. So we have the values, and here we should see the data frame. That's the data frame we have. So this is how we can use the interleave dataset. Now from the performance perspective, so let's look at the performance. So here what we are going to do is we are going to use the make underscore CSV underscore dataset and then the interleave and see how different methods compare. So for that we'll use the batch underscore size is equal to 2048 fonts underscore dataset is equal to tf.data.experimental.make underscore CSV underscore dataset open close parenthesis file underscore pattern is equal to fonts /star.csv comma batch underscore size is equal to batch size all uppercase that we have defined above, and number of epochs is equal to 1, and then number of parallel reads is equal to 100. So that's the data set fonts underscore ds that we have created. Now let's use time, and in here we'll use enumerate for I comma batch in enumerate fonts underscore dataset dot take 20 colon print, just going to print a dot and end is equal to nothing there, and after this is done we just print nothing. So let's see how much time this takes to run the for loop, and after that what we'll continue writing. So what we can do is pass batches of text lines to decode underscore CSV. So for that we'll say fonts underscore files is equal to tf.data.dataset.list underscore files, and fonts /star.csv. So this took around 25 seconds. Now let's try this. Fonts underscore lines is equal to fonts underscore files dot interleave, and here we have a lambda function that takes in a file name tf.data.TextLineDataset file name, skip the first row like so, and then we have comma cycle underscore length is equal to 100, and with this we can set the batch size. So we'll say bring this up here and say dot batch underscore batch is going to be batch size. Okay, so with that we'll run that, and now we'll use that for mapping. Fonts underscore fast is equal to fonts underscore lines dot map lambda lambda x colon tf.io.decode underscore csv x comma record underscore defaults is equal to, let's put this on a new line, record underscore defaults is equal to font underscore column underscore types, and with that you can close those brackets. And what am I missing? Fonts underscore, so that's this, put that there, check if all the commas are right, and that should be good on that. And okay, that's good. So fonts fast. Now we can look at the print type fonts underscore fast, and fonts underscore fast, what we see is the type of it. And so if we scroll all the way up, what we have now is a map data set and the tensors elements within it. Let's now time this. So create another cell, maybe a couple of cells, and in here we say %% time for I comma batch in enumerate fonts underscore fast dot take 20 print the dot, and we'll specify end is equal to 0, not 0 but nothing, then print from this, and this looks like this is much faster, and this takes 3 seconds as compared to what we had up earlier, which was 25 seconds. And so that's how, if there are larger batches, maybe the interleave could be an option to consider. That was it for this video. I hope in this video you got some intuition about how to load CSV datasets into the into pandas and convert them into the uh, uh, shape and format that can be used with Keras, and also use Keras utilities to import the CSV dataset, as well as using the tf.data to create datasets or that can be used as an input for the models. So if you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video as well. Please like, share, and subscribe, as it helps me stay motivated to create more content for you all. Again, thank you, and see you all in the next video.